that, I'm going to
Cancel class.
turn you loose a little earlier than normal. But it's not because you're a smaller group. My wife is picking me up at 4 o'clock to drive to Brigham City, Utah, where I will meet with my dad and my siblings. Well, 3 out of 4. No.
Happy birthday.
3 out of 5 of my siblings. And their spouses, and my kids, and their spouses.
Happy birthday.
One has a spouse, one not. But he's bringing his girlfriend.
Just for fun.
Just to help me celebrate my 60th birthday.
Oh, that's right. Your birthday's today, huh?
I just said that,
Oh,
Yes,
God.
it is.
It's so terrible.
as Adam pointed out.
No, Adam pointed out his own birthday.
So I am officially old, just so you know. Not so much.
Do we ever feel old?
And I think people feel old.
Well, you can't retire till after I graduate.
Not planning to.
Cool.
All right, so let us begin with our favorite learning activity.
We can't see anything really now.
What is the first question on your self-assessment for closeness?
Closeness or clearness?
Closeness.
Oh,
We've all done clearness.
well, we haven't looked at closeness yet.
You asked me to put the sample code out there.
Yeah, and I messed with the sample code.
So you've all seen this, right?
Sure.
Put that in a new tab. See, it's not very explicit about what I'm expecting. And the grading criteria, of course. Well, how are you going to earn your points for this one? I'll give you the right answers. You must have fun and learn something. These should look familiar. It's the same as on clearness, pretty much. Your output, you know, I'm gonna check. I'm gonna check on clearness and this one. Now, there's a lot of points to be gained to get it all correct. There are 22 tests to pass.
So
Nice.
We'll make it just do all of them in one go.
I will show you what Make It Just will do.
I did something yesterday.
Or you can type make dash
Maybe another
in
div thing or just like
close just.
see change.
Anyway.
What do you? Did you study on here before? 2:30. I gotta get over on that node sometime.
Let's see. Used to decide not to use yours today.
I already packed it up so I can just head out as soon as my wife is here. Console is 16. That's probably good. Okay. Yes, yes, yes. Well, let's look at what we have in the way of files here. Nothing. Forgot I got rid of those. So over in /home /CS238 files, you know, that's where you found your amortized files. which are still there, but there's these other files. And in fact, they're all in one, relations.in. So there's 1, 2, well, let's see, there's 15, 16 of those, and then 17, 18, 19, 20, 21, 22. What are these funny names for files? Well, you have, I believe, in 8.3, exercise 16, you ought, or maybe it's 8.1. Anyway, one of these looks like this. In fact, they all look like that. Cat 16.star. These are all possible connection matrices for a 2 by 2 connection matrix, right? There's 16 combinations of 4 bits from 0000 to 1111. So you got to test that. And then there's, it is 8.3 exercise 32, part A, B, and C, and then also exercise 8, part A, B, and C, to give 4 by 4 connection matrix. So you'll use these to test your relations code. Let's see if it works. We'll go to an exemplary solution and make it just. Okay, that means everything passed. And that's
So
what it
what if
says.
say like your transfer function's broken, then you'll fail all the tests?
Well, you'll fail some of them.
So does it stop or does it do all the tests and say you failed this and this and this?
I can't remember, but
It's not that big of a deal. Just wondering.
you know, we see what it does. So, it cats relations.in, that file. You can run these individually if you like, but it's running your program with those files one at a time on the command line and diffing it with this file, relations.out.
Well, that was just the way that you found out before which test it failed with when it said bad information.
Yeah, this way you'll know it's bad because you'll see lots of output. It won't match this. It's got to match this exactly.
Not non-symmetry. Not non-symmetry. Wow.
Here we go.
You know, there's a rule in writing called you should that specifies that you should never use double negatives. You should only use positives.
Yeah.
Well, you know
So
what?
you
It
should
makes
just use
easier code, so I'm okay
irreflective.
with this.
And mistakes.
You know that I don't buy into all these rules that you have to.
This is like,
Yeah, grammar, no worries.
well, he's writing the text.
So closeness CPP already has the grammar for you in the describe function.
Yeah.
You just have to implement the functions that say whether it is or isn't one of those things.
That's helpful.
Actually,
Okay.
I want to say that describe doesn't exist. Maybe I'm wrong.
No, it is there.
Oh, it's just a stub in the CLI.
Let's see, this is not where you'll find it. You'll find it over here. Sample code closeness. It's there.
Okay, I just saw the prototype.
Yeah, what's not there are all these functions. That's what you have to do. But that's not all. No.
Of course.
What else do you have to do? What else besides correctness and completeness? How
Do we
about
have to do
for
closure?
almost half of your total points? Elegance. 8 points per checkbox, so you want to make sure you get as many of those as possible. The last two are the hardest.
Yeah, I'd imagine so. Because a lot of them are really similar. Reflexive and anti-reflexive.
It's easy to do this part for, and the rest of it. Pretty easy to get the 52 points there. And, really you can get 60 points because that first one's a gimme if you get it all correct. And I expect most of you will get, at least 84 points. Probably even 92. Only the intrepid among you will get all the way to 100. That's just going by past semesters. And in the past, you didn't have quite as much detail. Let's see if I can find a, for instance, CS 238. Why don't I have my most recent one here? Yeah. Let's see if it's there. Exploration 3.
Wow, you did well in this class, man.
What am I looking for? Oh. That's all you got last time I did this. But I like it better the way I'm doing it now. Don't you?
Yes.
If you self-assess, I force you to do a little introspection, which is always good for you. Right? Absolutely. A little metacognition.
Depends on the amount of miscalibration.
Indeed it does. Well, are there any questions before we dive into 8.5? You should have already dived into it, right? You dipped your toe in, but it felt too cold, so you didn't want to dive in head first with both feet? So what is an equivalence relation? Don't all answer at once.
That's reflexive, symmetric, and transitive.
All right, so it's got to have those three properties. So is this an equivalence relation? Congruence mod 4.
Sure is.
That's one of Rosen's examples. In fact, he lists the equivalence classes by their canonical representative, but that's not the only representative of these classes, right? If we were to list them all, we'd have 0, 4, 8, 12, and so on. We'd have -4, -8, -12, and so on. In this class, where you mod by 4 and you have a remainder of 1, this class, of course, has a remainder of 2 when you mod by 4. And you get the picture how these classes work. We could choose any one of them to be the representative of the equivalence class. So I've got 4 equivalence classes under this equivalence relation. And in general, for congruence mod M, you will have M congruence classes. What about a relation that we talked about, this one, divides. So A is related to B if and only if A divides B. Is it reflexive? Does A divide A? Yes. Is it transitive? If A divides B and B divides C, does A divide C?
Yep.
So yes. Is it symmetric?
Nope. Not always. Yeah, it's not like AC.
So yes, it is antisymmetric, but it's not symmetric. Well, why do we care about these 3 properties? There's lots of properties relations can have. Why those 3? When we look at the digraph of this general relation with 3 elements in the set and all of the arcs, all of the edges are present, then we know it's an equivalence relation. Everything is related to everything else in this digraph. And it's reflexive by virtue of these loops. It's symmetric because we have round trips between each element. This is a double arrow, but it's just like having 2 one-way arrows. Yeah. So here's the vocabulary that you need, this notion of an equivalence class. So square brackets to indicate that this is the equivalence class of X. It's the set of all Y such that X is related to Y. X, Y is in the relation. And again, it's just a representative. Any one of them could be chosen. No democratic vote necessary. You don't vote on the representative, just pick one. What is this notion of the rank of an equivalence relation?
How many smaller versions there are that fit that relation?
Smaller versions, say we have A with 3 elements. There's 3 of these sets, subsets, where each element in the subset is related to every other one. And here we have rank 3, where it's just one element in that subset. Here's a rank 2. We have 2 elements in one subset, 1 in the other one. It's still an equivalence relation. Both of these subsets are. So there's another rank 2, another rank 2. There's one rank 3 that you already saw, right? And it's drawn a little differently with the 3 on the bottom, and we have both direction of the arrows for the others. Is this familiar? Does this look like you've seen this before?
Sort of. It reminds me of ECN 160. How we had the state graphs.
Yeah. I'm thinking a little further in the past. Maybe it's before your time, but I'm sure you've seen Back to the Future. I've seen pictures of the flux capacitor. That's what one student said when he saw that for the first time. That's the flux capacitor. You gotta love it. All right, so there's an equivalent notion, and this is in your book on page 561. Figure 1 shows it for n equals 9. So I have 9 subsets of a set S. It's defined to say we have a partition of S if this collection of subsets, if they are non-empty, disjoint, and exhaust S, those three conditions are what it takes. So non-empty, disjoint, and mutually exhaustive of the set. Do these sets form a partition of the integers? They're non-empty. They each have an infinite number of integers in them. They are disjoint. There are no elements in common with any of those sets, and union them all together and you get all of the integers.
It's also an interesting thought to think that not only do they together exhaust all of the integers, but individually they each have the same cardinality as the integers.
Yep, it's true.
But
All those paradoxes of
union all together, all four of them are all, if we split it into 100,000.
Yeah. It's a nifty phenomenon. You've seen it before, especially if you recall deepness and those two sets we called excursa. I've stopped calling it that in case
What do you
some
call
of my
it now?
237 students ask you.
What do you call it now?
It's not gonna tell us. We can't tell
I
them.
call them set A and set B.
That's so neat.
Mind games.
And so
We're doing Greek words.
we know that this applies. We know that A intersect B is the empty set, and A union B is Z plus. So they form a partition of the positive integers. But it's more interesting when you have more than two sets, which we do in the case of congruence mod M. So here's the theorem. The equivalence classes of an equivalence relation R partition the set into disjoint non-empty subsets whose union is the entire set. Well, what about this partition, this notion that we have S somehow divided by R, divided up into non-empty, disjoint, and mutually exhaustive sets? So we call it the quotient set, or the partition of S induced by R, or my favorite term, S modulo R. Gotta love it.
The shortest.
And that's, nodding to the congruence mod M, which is kind of the epitome of an equivalence relation. Actually, there's one relation that's even more of the epitome of an equivalence relation. That's equals. Symmetric, reflexive, and obviously transitive. But probably not very interesting when you talk about equivalence relations to focus on, equality. But here's the key point, what I want you to take away. Whenever you have a relation where something has the same whatever as something else, you have an equivalence relation. So Rosen's example of identifiers, variable names in older versions of C. You could have the variable name as long as you like, but the compiler only cared about the first 8 characters. So they essentially had a function that took the variable name and chopped it into 8 characters. Take the first 8 characters. Any variable with those same first 8 characters was considered the same by the compiler. Couldn't tell them apart. So you had to be careful naming your variables. That's not so in C++ and our modern compilers. It used to be that way. So anytime you have someone who has the same age as someone else, the same birthday as, the same name as, the same parents as, the same first 3 bits as, one of the exercises I assigned has something to do with that. Anything that you can say it's the same as, so the same authority as. Think of an example in the scriptures of an equivalence relation. priesthood in general, prophetic authority. Doctrine and Covenants 138. What I, the Lord, have spoken, I have spoken, and I excuse not myself. Though the heavens and the earth pass away, my word shall not pass away, but shall all be fulfilled. Whether by mine own voice or by the voice of my servants, it is the same. So the same whatever as. I did not assign this exercise, I don't think. Double check me on that. But it gives a way, in a very important way, to establish that some relation is an equivalence relation. So this is the text of the exercise. Suppose that A is a non-empty set and F is a function that has A as its domain. Let R be the relation on A consisting of all ordered pairs x, y such that f of x equals f of y. Well, it's trivial to show that that is an equivalence relation. Is it reflexive?
Yes.
Is it symmetric?
Yes.
Is it transitive? Trivially true. What are the equivalence classes of R?
The different
The equivalence
values
classes.
would be the codomain of f of the function.
So what is that called? It's not called the codomain.
The values it takes on.
What is the set of things that are equivalent under this equivalence relation? In terms of the function f.
Just the variables that you put into it.
What are those variables called?
The domain or the range or the inputs?
You don't remember.
I don't remember.
No, we don't.
The set of inverse images of the function f,
I would not
or
have
the inputs you put in, and you get the same output if they're in the same equivalence class. It's just like congruence mod 4. If that were a function, say f of x returns x mod 4, then f of 0 would equal f of 4 would equal f of 8. Any of those inverse elements, inverse images, would have the same result, the same value when you apply that function f to it. Well, here's the key point. This works for any equivalence relation. If you identify this underlying function, you have captured the essence of the equivalence of things. Mod 4. And any and all equivalence relations have this feature. So exercise 16 is another good example. I didn't assign that one, but it should call to mind something you learned in grade school or maybe middle school. Let R be the relation on the set of ordered pairs of positive integers such that the pair AB and the pair CD put together as a pair of pairs is in R if and only if AD equals BC. R is easily shown to be an equivalence relation. In fact, it follows quite readily from exercise 9, which we just have to identify the function. Well, this is a function from the set of pairs of positive integers to the set of positive rational numbers that takes the pair AB to A divided by B, the rational number A over B, since clearly AD equals BC if and only if A over B equals C over D. Isn't that true? If and only if.
Yep.
Easy to see because, 3/4 is equivalent to 6/8. 3 times 8, 24. 4 4 times 6, 24. So is this how you were taught fractions? You were taught how fractions work and, you know, what fractions are equivalent? You don't remember talking about equivalence relations?
I don't remember multiplying diagonals. Well, actually, I do. Solving proportions.
Yeah. So it's a way to identify identical or equivalent fractions. And it's, I have read an author, I don't know that his opinion is universally held, but he thought that if students were taught this way of understanding fractions, we wouldn't have any mathophobia about it, you know, especially with people who hate math because they never did understand fractions. Anyway, fractions may be called the same fraction if they reduce to the same a over b in lowest terms. So 3/4 is in lowest terms, 6/8 is not. Remember, we did something with fractions in lowest terms to prove that some irrational number was in fact irrational. Remember which one that was? Way back in 237. The square root of 2. And part of the proof by contradiction, wanted us to show that, or to assume that we had a fraction in lowest terms, because otherwise, you know, you could divide out the greatest common divisor of both of them and reduce it further until they were relatively prime and could not, well, the relatively primeness of those two means their GCD is 1, so dividing both top and bottom by 1 doesn't change it. And this way, we're guaranteed that both of them cannot be even, because if they're both even, you can reduce it. Well, it's one of many equivalence relations that you were probably unaware of, that it was called that. Are there others that you've encountered? Maybe even in programming. I don't know if Brother Burton moved this stuff around. I think he might have. CS246. There it is, Java source. We can find this online too, I'm sure. But let's just go to Java lang object, for example. In implementing a subclass of object, there's two things that you're asked to do, and that one is to override the hash code function. So there's a native method that gives you the hash code of a generic object, and you should, two distinct objects should produce distinct integer results, right? The other method is called equals. And let's see, we could search for, yes. So, I guess we could more easily look at this online. Where is our, yeah, let's just look at the documentation for it. Doesn't matter which version, it's been there from the beginning. The equals method implements an equivalence relation. Did you know that? If you say one object is equals to another, it better conform and comply with these properties: reflexivity, symmetry, transitivity. Where's another arena where equivalence relations are used, or equivalence classes even? Have any of you taken Software Engineering 3? What do you talk about testing in that? Or is that part of 2? So in Software Engineering 2, you talk about testing. Is it possible to exhaustively test code?
It's really small.
Yeah, it depends on what the domain of its inputs is, right? If it has an infinite domain, integers, say, even if it's a long type, and if it's got more than one input parameter, you have the compounding effect there. Not practical to exhaustively test, so pick a representative from the equivalence classes, the inputs that generate the same output. And then you only have to test one representative instead of many. So it is a notion that's very practical. And we're going to look at some. In fact, next time when we meet again on Wednesday, I'll invite you to ponder a recurrence relation that you heard about when you took the quiz for today, which you all did yesterday, right?
Sure did.
Sure. Well, we'll just see. I'll give you the answers. Well, you probably know them. All the good answers. Shortly after taking this quiz, I will have a closer look at exercise 68 on page 566 and ponder the derivation of the recurrence relation that purports to count the number of equivalence relations on a set within elements. Why that number is less than the total number of relations, Aliska?
What's reports?
Purports?
Yes.
Claims? Puts it forth as true, but, where's the proof? So, who can answer this question if you pondered it and have the answer? Justin?
Because all of this, the sets of all relations, the sets of all symmetric relations are on a set, are a subset of all the relations in a set. And so there's no way that it could be greater than the number of elements in the set.
So it's somewhere, you're saying it's somewhere between 0 and the number of total relations on a set within elements, which we saw was
2 squared.
But how you compute this number, the number of equivalence relations on a set within elements, is the question. How? We'll investigate that next time and kind of wrap up the discussion of equivalence relations. Probably start talking about partial orderings, subject of 8.6. Carry that on. I think we're going to be finished with chapter 8 next week, and then have another test. Woo! Yeah, keep them coming. That's what I like to hear. Bring it on. I'm ready. Well, have yourselves a great 3-day weekend. Don't spend all of it studying discrete math. But don't spend none of it either.